Okay, so I want to revisit this example too. We learned a way to do it, which is the way the book would describe to you how to solve this. And this is a good way. It was a little lengthy, right? The nice thing about exponentials is we can make a different equation that describes the same situation. The equation may look different at the end, but it will be the exact same model. And I think it might be an easier, or maybe not easier, but a faster way of finding it. Okay. The first thing we did, if you run through this, the first thing that we solved for was the value of k, correct? Down here, we got k is equal to natural log of 64 over 4. After we found k, we had to go back and find the initial value. So let's make this, what are we on, example 4? Let's make this example 4, but we're going to use the exact same example 2 right here. So rewrite it for example 4. The count in a culture of bacteria is 2 hours is 400. After 6 hours, it was 25,600. No. And what was it, 25,400? 25,600? 25,600 after 6 hours. The task was to find a model that gives the number at any time t. Now the model needs to be patterned after this. The amount at any given time t, a of t, is equal to some initial count a sub 0 times e to the kt. That's the model that we found last time on Friday. If you forgot what it was, let me just scroll over here. Sorry. Where are you? Where's our model? Did we even finish this?
Yeah.
Where is it? Oh, here it is. Our model was a of t is equal to 50 times e to the natural log 64 over 4 times t. So according to this, wasn't the initial count 50? I'm going to show you a little bit different way of doing this. We may have a little bit of a different initial count, and then we could mess with the time value a little bit. And it's going to end up being the same model, just in a different form. So the first thing we need to find is k, the growth constant, or the growth factor, the relative growth rate. Usually we do that by plugging in the initial count. Do we know the initial count? No. But we know that at 2 hours, how many were there? 400. And then after 6 hours, there was 25,600. So how much time has passed between 2 hours and 6 hours? 4. So if we put a 400 in for a sub 0 and a 25,600 in for the a of t value, and then this is going to be times e to the k, what time value we're going to have to plug in here to allow 400 bacteria to grow to 25,600? 4 hours. So we can put a 4 right there. So even though this a sub 0 isn't the actual initial count, okay, we're still going to be able to solve for the growth factor k using the information in the equation. Now how do we solve for k? Divide by 400. 25,600 divided by 400 is 256 over 4, which is 64. So this turns into 64 is equal to e to the k times 4. Now everybody stop for just a second. I want to make sure we're all on the same page. Normally a sub 0 is the overall initial count. But if we just backtracked everything by 2 hours, we could consider this to be some kind of an initial count, 400. And then between 2 hours and 6 hours, how much time has passed? 4 hours. So we could consider 400 to be some initial count and then allow 4 hours to pass. If 4 hours have passed, if we start with 400, it's grown to 25,600. So we take the natural log on both sides, and we get the natural log of 64 is equal to k times 4. Divide by 4 on both sides, and we get k is equal to natural log of 64 over 4. Now compare, if you're looking at your original notes from last time, compare. K is the same.
So much easier.
Now, the only difference is you got to be careful. Please try to listen carefully to how we form our model. Okay? Even though k is the same, the model that we're going to use now is going to look a little different than the model that we formed last time. So, a of t, I'm still going to consider that value of 400 to be our a sub 0. Even though that's not the overall initial count, I'm still going to allow a sub 0 to equal 400 times e. Now we know the value of k, natural log of 64 over 4. But, and make sure you write this very carefully, this is the initial count after 2 hours. So you have to take 2 hours away from the time value.
Is it for me? Is it for me?
One of these days I'm going to get a note from my mom excusing me to go home for the rest of the day.
That day's not today.
That day's not today. Let's talk about this. Okay? And let's compare this model to what we ended with. Where are you? Right here. This is the model, which is a correct model that we ended with last time. A of t equals 50 times e to the natural log of 64 times t. Because this is when t equals 0. When t equals 0, how much do we start with? 50. Because if t equals 0, what's the natural log of 64 over 4 times 0? 0. And what's e to the 0? 1. And what's 1 times 50? 50. So when time equals 0, how much do we start with? 50. That's the initial count. Compare that now. Okay. After 2 days, according to this information, after 2 days,
2 hours.
after 2 hours, after 2 hours, how much bacteria should there be? 400, right? After 2 hours, shouldn't there be 400? Let's see if this model is accurate then. If we allow time to equal 2, what's 2 minus 2? 0. Okay? What's the log base 64 over 4 times 0? What's e to the 0? 1. 1 times 400. So if we allow t to equal 2, shouldn't that mean that there's 400 bacteria? Isn't that what we have? After 6 hours, how much bacteria should there be? 25,600. So if we allow t to equal 6, what's 6 minus 2? 4. Now, if this becomes a 4 right here, that 4 cancels with that 4. You following? Now, if the 4 is gone, then what about e raised to the natural log? What happens there? Those cancel, so now it's just 400 times 64. Somebody with a calculator, quick, type in 400 times 64. It's 25,600. So far, is this model accurate based on the information? Natural log of 64 over 4. I'm just curious if we all understand, why do we have to have a time value of t minus 2?
There should be.
Oh, there should be an e right there. Because this initial count is after 2 hours. And that's fine to use this initial count, but then we have to take off 2 hours from any time value that we use. Okay? So this is another valid model that fits the data. Okay? I know it looks different than the model we came up with, and that's the nice thing about exponentials. If you're trying to fit an exponential model to data, there's not always just one model that can model it. Okay? So there's another way that you could have done this. There's actually a third way that we're going to learn in chapter, I think it's 11. The other way we can model exponentials doesn't even involve a base of e. It's a little bit different. So anyway, let's do one more radioactive decay, and then we'll get into logarithmic stuff. So this is example 5.
Let's have thorium.
We need another radioactive isotope.
Thorium.
Thorium? You're making stuff up.
No, thorium is a real element and it is radioactive.
There's an element called thorium?
Yeah.
Is it named after Thor?
Yes.
That is awesome. Do you happen to know the half-life?
No.
Well, I'm going to stop this. We're going to Google it.
You can search it on Google though. No, that's the time. That's the age he makes when he has his midlife crisis.
The half-life of radium. Did we already do radium? Well, let's do cesium then. Cesium. And the isotope is 137. The half-life of cesium-137 is 30 years. That's a nice number. Yeah, 14 billion. Suppose we have a 12-gram sample. Find a function that models the amount remaining at any time t. The nice thing about all of these exponentials, even the ones dealing with money, the continually compounding interest, they all essentially use the same model. It's a of t, the amount at any given time t is equal to the initial amount, a sub 0 times e to the kt. And just since we were barely on the subject, what's the corresponding equation if we're dealing with money? Continually compounding interest. P, a is equal to p times e to the rate times time. They're very, very similar. Okay? So anyway, you need to remember both of those for the test. Yeah?
Is that formula applied to every single problem on the board?
This one here? Anyone that deals with exponential growth or decay, not logarithmic growth.
We're not going to be talking about that, are we?
Logarithmic? Yeah, oh yeah. Not logarithmic growth, but applications involving logarithms. Specifically the pH scale and the Richter scale. So anyway, we still don't know that relative growth rate, the value of k, but we do know an initial count. There's 12 grams. And if we allow time to equal 30 years, that's a full half-life. If we allow a full half-life to pass, what's the remaining mass of the sample? 6. So what we're doing now is to solve for the relative growth rate, and then we can finish our model. Divide by 12 and we get 1/2 is equal to e to the k times 30. Yeah? Because if we allow a full 30 years to pass, that's one full half-life. So 12 grams would have been reduced to 6.
Got a 1/2 on one side.
Does that answer your question? Okay. And then we divide it by 12 to get that 1/2. Now if we take a natural log, we have natural log of 1/2 is equal to k times 30. I know I'm moving pretty quick here, but I'm really excited to get to this pH stuff. Divide by 30, and we have k is equal to the natural log of 1/2 over 30. So that's the relative growth rate. So now we can finish our model. The amount at any given time t is equal to the initial mass of the substance, which is 12 grams, times E to the natural log of 1/2 over 30 times t. Using that model, scientists could predict the remaining mass of the substance at any given time, not just an interval of its half-life. Let's move on. Logarithmic stuff. We're gonna do the pH scale, and then we're gonna do Richter scale. Both are logarithmic scales. Richter? German.
Someone's last name.
So pH. Okay. pH is equal to negative log of H plus. How'd you know that? Oh, did you? Cool. The pH of a substance is equal to the negative log of its hydrogen ion concentration.
In neutral pH is 7.
Yeah.
Acidic ones are lower than 7, and basic ones are higher than 7.
Yes, you are correct. Where H plus is the concentration of hydrogen ions, and that's measured in moles per liter. I'm sure you chemists know what that is.
Not yet. We're learning about moles eventually.
Exactly. We're going to use scientific notation.
I remember the song.
I would forget.
What song?
Like 6 times 10.
Oh, actually,
So, in case you're a little rusty with the pH scale, it's a scale ranging from 0 to 14, I think. Anything less than 7. 7 is considered neutral on the pH scale, meaning it's neither acidic or alkaline.
That's what one
Distilled water is 7. Anything less than 7 is considered acidic, like battery acid or stomach acid, lemon juice. Coca-Cola is actually pretty low on the pH scale. It's like 3.5. Anything above 7 is a base. Soap, possibly. I don't know. I'm not too familiar with the bases. It says here, just in the book, human blood has a pH between 7.3 and 7.5. Seawater is about 8. Milk of magnesia, whatever that is 10.5 on the pH scale. Anyway, let's do an example.
So baking soda and vinegar react so violently. One of the acid and the base.
Is this one going to be a long example?
Yeah.
Can I use 3 lines?
Sure. The hydrogen ion concentration of a sample of human blood was measured to be H plus equals 3 Now the reason that we're using scientific notation, the hydrogen ion concentration measured in moles is an extremely small number. So it's 3.16 times 10. Well, that's the pH, but this is the hydrogen ion concentration. Now, here's the reason for this pH scale, you guys. the range of hydrogen ion concentrations in any substance is gigantic. Okay? The range could go from 3.16 times 10 to the negative 2 to 3.16 times 10 to the negative 12. I mean, there's a ginormous range of numbers for hydrogen ion concentrations. But using a logarithmic scale, it shrinks the range significantly. Here's what I mean by that. It's kind of a hard thing just to listen to and understand. But let's say that we have a range of numbers. We have 1, we have 10, we have 1,000, we have 10,000, we have 1 million, and 10 million.
Then 100 million.
That's a pretty large range of numbers, right? Between 1 and 10 million. But what if we considered the log of each of these?
Give me 100 and 100,000.
I know. But what if we took the log of each one of these numbers? What's the log of 1? 0. What's the log of 10? What's the log of 1,000? 3. What's the log of 10,000? What's the log of
6.
what is that? 1 million? 6? 10 million? So, you guys, you really need to try to understand the power of these logarithms. We've taken a range of numbers from 1 to 10 million, and simply by taking the log of each one of them, look at the range of numbers now. It's from 0 to 7. And that's what the pH scale does. It takes a range of numbers that has a huge span, but when we take the logarithm of each of those numbers, the span shrinks. Now it's between 0 and 7. Does that make sense why the pH is measured in logarithms? Because to describe something in terms of its hydrogen ion concentration is very cumbersome, but to describe it in terms of its pH, much easier. So, we have H+. The task is, what is the pH? Okay, well, pH is equal to negative log of the hydrogen ion concentration, H+. And we know the hydrogen ion concentration. So pH is negative log of 3.16 times 10 to the negative 8. This is another reason why this type of logarithm is called a common logarithm. In scientific notation, it's always going to be some kind of a number times 10 to some power, correct? Why is it always times 10? We have a base 10 number system. If we times anything by 10, it moves the decimal either to the right or to the left. So quite often we're going to use a common log because in scientific notation it's always times 10. The pH one I'll give you. You have to know the ones dealing with exponentials. I'll give you the equation for pH. I'll also give you the equation for Richter scale. Anyway, we're going to have to invoke the law of one of the logarithms we learned about. What type of a thing are we doing inside this logarithm? We're multiplying, right? Isn't this a product? It's 3.16 times 10 to the negative 8. So this is equal to negative. Now notice I put this in parentheses because we're expanding. So this is negative log of 3.16 plus log of 10 to the negative 8. So now this is equal to negative log of 3.16 minus log of 10 to the negative 8. The reason I put that in parentheses is so you remember that you had to distribute that minus sign. So now both logarithms are negative.
Now you can use the negative 8 up to
Exactly. Now since this has an exponent of negative 8, that can move down to the front, but there's already a minus in front of that logarithm. So it's changed to positive, so this becomes negative log of 3.16 plus 8 times the log of 10.
Log of 10 is 1.
Log of 10 is 1, exactly. Log of 10 is just 1, so this turns out to be 8 minus log base 10 of 3.16. Now, you are going to have a test question that deals with this type of a pH scale. and I'm going to give you the approximate value of whatever logarithm you're going to need. For example, in the initial part of the problem, I would have given you this in parentheses. Log of 3.16 is approximately equal well, let's see.
Cheater, cheater.
0.499.
Is there like drugs?
You said you know.
So this would have been information given to you in the problem. So now you can actually finish this and get a more accurate pH reading, because right now this is where we would have to stop because we wouldn't be able to go any further. But if log of 3.16 is equal to about 0.499, this turns into 8 minus 0.499. So 8 minus 0.499 is approximately equal
511 or 521.
and that's the pH. So it's a little larger than 7. 7's neutral, so what do we call this one? It's a base. That's how all of them are going to work. If you're given a hydrogen ion concentration, you can run it through this little pH algorithm to find its pH. Let's do one more quick one, then we'll get to the Richter scale. Part B, sample of seawater. Has a hydrogen ion concentration of 5 times 10 to the negative 9 molar. So find the pH. Oh, you also need to know this. Put this in parentheses. Log of 5 is approximately equal to 0.7. Approximately equal. It's 0.6999. I figured I'd take it easy on you.
No, I already know
So
the
nice.
pH of the scale now. I'm pretty sure. I'll go through it. Maybe I know.
Okay. I dropped the negative 9 down in front, which changed it to a plus, so it's plus 9 times the log of 10, but this is a common log, which has a base of 10 already, so that simplifies to 1. 1 times 9 is just 9. So we have 9 minus log base 10 of 5. According to the initial information, the log of 5 is approximately 0.7. So if you take 0.7 from 9, you get the approximate pH of what? Of about 8.3. All right. So that's pH scale. It doesn't really vary so much from that. On your homework, the latter part of you're gonna have to go backwards. If you already know the pH, you're gonna have to go backwards and find the hydrogen ion concentration. If we have time after we go through the Richter scale, we'll do one of those. Let's do Richter scale.
might be, that pattern might not always exist.
See if it does when you do the homework.
Okay.
Okay. And we can talk about it on Thursday. All right, Richter scale was developed by a guy named Richter. Yeah. It measures the intensity, or the magnitude rather. It measures the magnitude of an earthquake. So magnitude M is equal to the log, common log, now magnitude or earthquakes can be measured differently. If it's measured with a seismograph, that measures the intensity of an earthquake. The intensity is the distance between the amplitude. You guys have seen a seismograph, right? It's this little needle that goes up and down. Have you seen, you know what I'm talking about? That measures the intensity. They measure the intensity based on the amplitude of the little wave thing that's being made. Can you all visualize that? From that, then they could calculate the magnitude of the earthquake using this. So the I stands for the intensity of the earthquake that they're measuring. And then you divide that by what's called S. S is the intensity of a quake that's barely noticeable on a seismograph. Some earthquakes are so small that they don't show up on a seismograph. So S stands for what's called the intensity of a standard earthquake. This would be some kind of an earthquake that barely registers on a seismograph. That could be a large truck. Could perform enough earth movement to be barely noticeable on a seismograph. So it doesn't have to be a huge, gigantic earthquake. So that's the scale here. Magnitude is equal to log divided by, or log of I over S. Okay. Let's do an example. What example are we on? 7. If you had to choose a city in the United States that's picked on with earthquakes, which would it be? San Francisco. Let's pick on San Francisco. In the 1906 San Francisco earthquake. No, this is information from the book. Had.
I thought the earthquake was a little bit earlier.
It probably has an earthquake every year. Had an estimated magnitude
That's a big one.
of 8.3. On the Richter scale in the same year. An earthquake occurred in Colombia that was 4 times as intense. Now, and again, here's the reason for using a logarithmic to talk about magnitudes of earthquakes. The intensity of earthquake could be a huge span. It could be a very small number. It could be an extremely large number, okay, in the thousands or tens of thousands. So rather than saying, well, that's an earthquake that had an intensity of 928, that one had an intensity of 4,642, the scale of numbers is way too large. If you take a logarithm, it shrinks down the scale. What is the scale of the Richter scale? Between 0 and 10 really is about as high as they ever go. So the Richter scale shrinks the range of numbers significantly.
Wasn't there a 12?
I've never heard of one. According to this table in the book, the largest one.
There's only one because the scale only goes, like, the biggest of infinity, basically. So, like, the log base something of infinity.
That's only the scale. The scale would continue, but it can't continue because it's infinity.
If Chuck Norris fell off his bed,
Well, that's
and
the exception.
we might have a 12 magnitude earthquake. But according to this, the largest magnitude earthquake on record is in Chile, measured 9.5 back in 1960. So the Columbia one was 4 times as intense. What was the magnitude of the Colombian earthquake? These are done in kind of a peculiar way, but the more you do with these, you do it the same time every time. It's just you got to get used to how this is done. We already know some initial information that San Francisco had one that measured 8.3. Okay, so let's do San Francisco right over here. The magnitude of the San Francisco earthquake was 8.3, and according to the Richter scale, that's equal to the log of I over S. We don't know the intensity, and it doesn't matter what the intensity of a standard one is. The Colombian one, what's the only thing that we know about the Colombian earthquake? It's 4 times as intense. Now, does that mean we just take the magnitude and times it by 4, so it's a magnitude 24 on the Richter scale? No. What do we multiply 4 by? The I. Okay? So the magnitude of the Colombian earthquake is equal to log of 4 times I over S. Now, why are we multiplying the I by 4? Because it was 4 times as intense, right? We can solve this without knowing the actual intensity, nor do we ever have to know really the standard intensity of an earthquake. That doesn't really ever matter. What does matter is your knowledge of manipulating expressions. This 4I over S, we need to write this a little bit differently, 4I over S. Can anybody think of a different way to write 4I over S? I think I heard somebody say it. 4 times. Do you guys agree that these are the same? They are the same. I don't care if you agree with me or not. They are.
That's a different way. I expanded it.
That's what we're actually gonna do. So now we have log of 4 times I over S. Why would we want to write it as 4 times I over S? What did we learn back in section 4.4? We can expand them using laws of logarithm. This turns into log of 4 plus log of I over S. You can, you certainly can. But what is the log of I over S? 8.3. We define that using the San Francisco earthquake. Log of I over S is equal to 8.3. Did you have a question on this one?
Oh, no, sorry.
Oh, you said you were so confused.
Oh, I was talking about...
Well, focus here on this.
I am confused. It was Gentry. She texted.
Gentry.
Oh. You guys didn't make her.
So this is a log of 4 plus.
She said my mom loves me more.
Now I'm confused.
I texted her and told her that her mom loves me more than her mom loves me more.
Anyway. Okay.
Anyway, continue.
Log of 4. This would be another one of those things where I would give you the values you would need. The log of 4 is approximately 0.6. So this turns into 0.6 plus 8.3. So what is the actual magnitude of that Colombian 8.9? It's the magnitude 8.9 on the Richter scale. Yeah?
Wait, why don't you draw that arrow?
because we defined the log of I over s to equal 8.3. Log of I over s is equal to 8.3. So we replaced this with 8.3.
Dang, so like, just a couple points does actually make a big difference.
Yeah. Now that's actually what I wanted to talk about. A couple of points difference on the Richter scale. The difference between like a 7 and a 7.5 in terms of intensity, that's quite a bit more intense. Okay? Now, to increase one full, you guys, to increase one full number on a Richter scale, like to go from 6 to 7, how much more intense is that? 10 times as intense. If we go from a 5 on the Richter scale to a 7 on the Richter scale, what is that? That's 100 times intense. So small movements on the Richter scale equal giant leaps in the intensity of the earthquake. So, and again, that's why the Richter scale is so nice, because intensities range a lot. Richter scale doesn't really range. I mean, it goes from 0 to 10. So that's about all we have time for.